you hear?
Yes.
Okay, so it's your time. You can start.
Yes. Thank you, Chairman, and thank you for thank the organizers for giving me opportunity to join this very interesting workshop through online. And my name is Atsushi Fujimori, University of Tokyo, and now frequently working in Taiwan, National Tsinghua University and National Synchrotron Radiation Center. And these are my collaborators with Dijin Huang and his collaborator in Taiwan photon source. And this work has been motivated by theoretical input by Masa Imada and his co-workers, and the sample from Professor Watanabe's group in Yosaki University and funding agencies from Japan and Taiwan. Okay, so this is our outline of my talk. So after a brief introduction about cuprates, what the problem is. Actually, the problem is the origin of the pseudogap, and then I will discuss one by one based on spectroscopy and other published data. So this is a well-known crystal structure of cuprates and phase diagram. In addition to the Mott insulating state and superconducting phase, there is a so-called pseudogap phase in which the density of states at the frame level is partially depleted when you go from overdoped to underdoped, and the pseudogap opens in the antinodal direction and leaving disconnected frame surface, so-called Fermi arcs, and further underdoping, it finally vanishes. And why do we care about the pseudogap? Because in many high-temperature superconductors or unconventional superconductors, some kind of ordering, anti-ferromatic, CDW or charge order, their endpoint or quantum critical point is associated with the superconducting appearance of superconductivity. But somehow in cuprates, the origin of this ordered state is not clear at all. So let's look at, there are several candidates, superconductive fluctuations or charge order, enigmatic order. And in my talk, I will focus on this viewpoint. But let me look at this one by one. First, superconducting fluctuation. This is something like a few tenths or several tenths Kelvin above the TC. There are still order parameters are fluctuating. It has been seen in many transport, optical, and experiments. But obviously, the pseudogap region is very wide, and this alone cannot explain the entire pseudogap phase. Then charge order, or ordering of the charge density, or very frequently, not only charge, but Cu Cooper pair density wave order in periodic order in real space has been discovered and discussed. This is something like modulation of charge density. So translational symmetry is broken by this density wave. And this is such a transitional symmetry breaking can be conveniently studied by scattering or diffraction experiments of X-rays, as well as neutron scattering. And I focus on the resonant inelastic scattering. And resonant means X-ray is tuned to the core to conduction band absorption, and then this core is filled by this electron, occupied electron, ending up with the electron hole pair. This is in the spectra, electron hole pair excitation is seen at high energy, like 1 to 2 EV. But for the charge order can be studied by elastic part. This is an example of charge order or scattering intensity as a function of momentum transfer and lost energy. At zero energy, elastic part shows a peak at around 4 lattice spacing. So this charge order is in many cases 4. Of course, this periodicity changes with doping or between different systems. This is a summary in this review article that the charge order occurs below this dome for Bismuth 2212, YBCO, and CO. So this means charge order state is enclosed by the pseudogap phase. Sorry, I put another pseudogap line because ARPES always indicate this kind of pseudogap, or Nelson effect also. But some other transport properties show this T star line. And so charge order state is occurs within in most cases within the pseudogap, but ordering temperature depends on material very significantly, so that charge order by itself cannot explain the pseudogap phenomena, but the pseudogap, you can say pseudogap promote charge ordering, but to different degrees depending on the material. So nematic order has been intensively discussed. This is ordering, something like this. Translational symmetry is not broken, but 4-4 rotational symmetry is broken. So it is, in other words, this is intra-initial symmetry breaking, which means 2 oxygen atoms becomes inequivalent after this kind of nematic order. So we have done ARPES experiments, but let me skip of YBC BISCO under uniaxial strain. But let me just show the results. The symmetry breaking occurs in the pseudogap phase, and symmetry recovers in the normal metal phase, as well as in superconducting phase. So far, there are a lot of other measurements, elastoresistivity measurements. I will not explain in detail, but from these measurements, electronic anisotropy is induced in this blue region. And this is magneto-torque measurements. By torque measurement, one can measure magnetic anisotropy within the plane. So this blue part, broken symmetry part, is within the pseudogap phase, or even coincide with the pseudogap phase boundary. So this looks like nematicity is closely related to the pseudogap opening, and include the charge order or PDW state. But neutron nematicity measured by neutron scattering, inelastic neutron scattering, this elongation of one peak is occurs at quite different temperature. And also this high temperature, low doping region, the origin of the pseudogap is not clear at all, because symmetry breaking occurs in this region, but stopped in this high temperature, low doping region. So then let me, in the remaining time, let me explain the electron fractionalization. This is electron fractionalization means one electron split into two particles, like one-dimensional system, quantum Hall effect, or and Mott insulating state is also a kind of electron fractionalization, or electron band is split into upper and lower Hubbard bands. But further fractionalization can be considered as a for Hall system. The lower Hubbard band is split into lower Hubbard band and in-gap band. Actually, this is a numerical calculation of the Hubbard model, two-dimensional Hubbard model, show split by Hall doping, lower Hubbard band. This one is split into lower Hubbard band and in-gap band, like I indicated here. And this lower Hubbard band cross the frame level and create a so-called Fermi arc, as experimentally observed. So this can be modeled by the so-called this red part, red stuff is so-called the zero of the green function, which is called dark fermion in this theoretical work, because of the many-body interaction, the Green's function have this zero of the Green's function, and then zero Green's function and original quasi-particle band are hybridized and form bonding and anti-bonding state, which is nothing but the lower Hubbard band and in-gap band. This is so-called two-component fermion model, and can easily explain the pseudo-gap opening between the anti-bonding band and lower Hubbard band. And this is a cartoon picture of this situation. Mott insulator has lower Hubbard band is split by hole doping and creates a pseudo gap, which is quite large compared to the large and asymmetric, which is quite different from the more conventional view that pseudo gap is electron hole symmetric, but actually quite asymmetric. This is not a proposal, but the results of the numerical calculation. And so Premier arc can be also well described. And using RIXS again, resonant scattering, one can measure electron hole pair excitation. So in this view graph, excitation of an electron from here to here create electron hole symmetry with a finite momentum and finite energy. And so this is quite different from the this electron hole symmetric situation. So that below superconducting TC, below TC, pieces gap open. So above and below TC, electronic structure in this region is quite different, and pseudo gap and superconducting gap competes, unlike conventional electron hole symmetric pseudo gap. So this is a calculation of ARPES at pi zero. Probably this is well known, but the RIXS at pi zero and the finite energy. This is not very clear, but the enhancement, there is an enhancement in superconducting state, which is sufficiently large to detect experimentally. And these are experimental data of such electron hole pair excitation at energy of about 1 eV and momentum pi zero. And these are quite well explained by simulation. And okay, we have made a detailed temperature dependence study. But so to summarize, so this part, because using such a very large anti-symmetric gap, this pseudo gap can survive up to very high temperature and low doping. So probably this part can be explained in this way. Maybe not only in this region, but this effect is extended to a wider region of the phase diagram. So, so thank you very much for your kind attention.
Thank you. There's time for one question. Yes.
Thank you very much for the nice talk. I have a question. So these dark fermions or fractionalized fermions have been introduced to describe or model the self-energy of these cluster DMFT calculations by Imada. Now, is there anything in the theory, or is there anything in experiment which is beyond a mere basic spin fluctuation opening of the pseudogap?
Fluctuation of what?
So these dark fermions, so in these cluster DMFT calculations, you have spin fluctuations, and Masa Imada modeled it with these dark fermions. But is there any smoking gun to discriminate it either theoretically or experimentally against more standard spin fluctuation theories?
Yeah, this is a kind of spin fluctuation because four-site, actually cluster DMFT means four-site cluster in which spin correlation between neighboring spins are strongly antiferrometrically correlated, and low spin energy fluctuation, which is directly responsible for superconductivity, is not very clear from this calculation because the cluster is small, but successfully explained the high energy part of the pseudogap, I think.
Okay, thank you.
Okay, thank you very much. Let's thank the speaker again.
Thank you. Thank you very much.
Let's move to the next online speaker, Anthony Bollinger. Yes. Do you hear us?
Yes, sir.
Okay, good.
Let me share the screen. We'll get started.
Great. You have 20 minutes.
Thank you. Okay. So just wanted to say good afternoon to everyone, or morning, depending on where you're listening from. I just wanted to start with a quick thank you to the organizing committee for the opportunity today to speak, and especially for accommodating me by allowing me to present remotely. I certainly wish I could be there with you in person. It's been a few years since I've been able to make it there to that conference, and I have very fond memories of it, and I hope everyone's off to a great week. So I'm a member of the research staff in the oxide molecular beam epitaxy group at Brookhaven National Laboratory in the US, which is led by one of our session chairs today, Dr. Ivan Bozovic. Other members include Shihe, who is a scientist in our group and does a lot of the molecular beam epitaxy thin film growth. He's giving a talk, I believe, on Thursday to talk more about some heterostructures that he's been working on. Roberta Caruso, of course, just spoke almost an hour and a half ago about some of the work going on in the group. And Xiao Tao, who did his PhD work with us from University of Texas at Dallas, out of Xiaoyan Shi's group, and is now a visiting scientist with us, gave a really nice talk just a few minutes ago. So as the name would imply, oxide molecular beam epitaxy, we synthesize thin films by molecular beam epitaxy. This is our MBE machine at Brookhaven, which I think you've probably seen a few pictures of that already today. Xiao Tao gave a real nice overview describing how the films are grown. So I won't go into too many of those details, but just in case you missed his talk, I did just briefly want to point out that this system was designed for atomic layer by layer growth, as well as combinatorial growth and continuous operation. The chamber has space for 16 sources, and each of these sources is calibrated by a quartz crystal monitor before each growth to determine absolute deposition rates, which in turn are calibrated by Rutherford backscattering and other techniques. And this rate information then is used by the computer that controls the growth and controls the pneumatically actuated shutters that are on each source to meter out a precise amount of material to the substrate surface, and helps us to control the growth very finely with less than 1%. The chambers fit with a few analytical tools as well. READ, which gives some crystallographic information, standard for molecular beam epitaxy systems. We also have a time of flight, ion scattering, and recoil spectrometry system, which gives some chemical information if needed. So you pair all that with the most important ingredient, which is the years of experience gained interpreting the data coming from these tools and steering the growth. And we have a system that allows for atomic layer by layer growth. So, over the years, we've worked on materials from various oxide families, but we are chiefly interested in the high TC superconductivity, and so we mainly focus on the high TC cuprates. And we all know these materials display a variety of behaviors besides superconductivity. Depending on their doping, you can have observed magnetic ordering, normal and strange metal behaviors. You can draw lines on that phase diagram corresponding to spin density waves and charge density waves. And we've always been interested in exploring these behaviors in our group. But we also like to take advantage of the inherently layered crystal structure of the cuprates, as well as the atomic layer by layer growth mode in our system to explore some somewhat complicated, more complicated structures than just single phase thin films, such as some early and exhaustive work that the group performed exploring, say, interface superconductivity in cuprate metal insulator bilayers. I'm not going to really revisit that work here today. The references are here if you're interested. But rather, I wanted to talk about devices with multiple layers. And this is ongoing work. So the talk will really be focused kind of on what we've done, what we're doing, and then what we'd like to do in the short-term future. So one of the structures that we're currently interested in and are working with are tri-layer junctions. So some early work by Yvonne and others on superconductor insulator, superconductor sandwich type junctions showed some very interesting and important results. The structure of their devices is shown there in the left, which consists of optimally doped lanthanum, strontium, copper oxide layers separated by a single unit cell of insulating lanthanum copper oxide. And what was observed is that although the barrier is extremely thin, it prevented any supercurrent from flowing from one side of the junction to the other. And just to be clear, this is in C-axis. Heterostructures of the opposite configuration, so in graph here on the right, where a single unit cell of optimally doped LSCO was sandwiched between thicker layers of insulating LCO, confirmed that the superconductivity in the LSCO was not somehow killed by the LCO, artificially increasing the thickness of that insulating barrier. And so really is this tiny layer really is a very effective barrier against transmission of supercurrent from one side to the other. So we recently revisited this kind of SIS geometry, not really expecting that these junctions would act as say Josephson type junctions, but more like a normal tunnel junction, since clearly from that middle graph there, not all the current was expected to be blocked. And so what I'm showing here then are some films that were grown for this study. So this is done with Doug Natelson's group in Rice University. The kind of nominal structure is shown there to the left, which includes layers of LSCO separated by just a few monolayers of LCO. So the center picture is then some cross-sectional images. This was done by Ime Zhu's group. I believe MG Han was the one that took these pictures for us using an aberration corrected high angle angular dark field STEM. And then on the right, we're showing the strontium and lanthanum signals using atomic resolution EDS and high resolution EELs. And so we see nice, interfaces between the different materials here. And what we measured then were, well, first they were patterned into some kind of tunnel junction structure, the films were. So this is kind of just a cartoon, obviously, picture on the left, very similar to what was done in the past. These types of devices are made by first doing a lithography step, which pattern transfers the overall device geometry into the film, and then defining a mesa structure in the film. So that's the step C here in that diagram to the right. And that requires a very controlled, precise etch so that we stop somewhere in that bottom electrode region, while obviously not blowing all the way through it or causing any extra damage that would render it ineffective for transport measurements. We need to make some contacts then to the bottom and top electrodes. And so that's going to require some kind of insulating layers to be placed around the mesa so as not to short the junction. So that's done in D, and then the contacts are evaporated and lifted off there in step E. And Doug Nelson's group is really good at doing noise measurements. So that's one of the things that they were looking at. So the data I'm showing here on the left in panel A is for a film where the lanthanum, strontium, copper oxide layers had a doping of 0.15, close optimally doped. And that A panel shows a hall bar, which was fabricated at the same time as the tunnel junctions, showing that the film had good TC, good superconducting properties. The differential conductance measurements then of the tri-layer is shown there in panel B as a function of temperature. And it's clear from there we have a conductance suppression near zero bias. And the important thing, though, is there's panel C, is that there's definitely no supercurrent over several orders of current and voltage range at the lowest temperatures, or any temperature really. So these junctions clearly don't have any kind of Josephson coupling from one side to the other, but they are useful for tunneling experiments. And the group at Rice looked at specifically the noise measurements, noise level coming from these tunnel junctions, and that's shown then here, for example, in these right panels. So here, A, B, C, D, we see the noise spectra taken at different temperatures, and then the red dashed line is a plot of the expected noise level